Hello all, welcome to the course AI driven perception learning and mapping for drones. This is the 6th lecture, Foundations of Neural Network Multilayer Perceptron. So let's start with a curve fitting example. We observe here that there is a curve in green. In this particular example, let's take X as the input to the learnable algorithm. Let's take T as the corresponding ground truth or something that the model needs to predict, right? So let's make the data set as 10 training points, which is consisting of blue circles as we can see here. The goal is to learn data to predict T from any new X. So for example, we see different blue color training data. Let's assume I have a test set which consists of X cap, right, and it could be at various points in the curve. Compared for each of these X cap, which is the test set or the new unknown points, we would want to identify the correct T, right? So that is the goal. Now the task is to predict real value T from an input X, and essentially initially to train using this particular input, and then for any X like X hat, right? The true function is sin 2 pi x. However, this is unknown to the model. This is just for our understanding of this particular curve, right? Okay. Now the data generation essentially are points sampled from sin 2 pi x with some random noise added throughout each sample point. So we can observe that these points do not always lie on the curve. They are slightly shifted either upwards of the graph or below the graph. So the training point can consist of n input points from x1 to xn. Corresponding targets is from t1 to tn. So for each input we have a corresponding target, and the way we have generated the data is we have 10 points which are uniformly sampled from 0 to 1, as we can observe in the graph, right? The key idea is essentially the model should learn how this matching is done from the input X to its corresponding ground truth, and once it's learned this from the training set, we want to then see if we can generalize to test data, which can be denoted at X cap, T cap. Okay, so now let's also understand what do we mean when we say an error, right? So we can see that the model output is given as y. Okay, so let the predicted output be denoted by y. So y x comma w is w0 plus w1x plus w2x square and so on. So essentially the model that we are using here can be written in this particular equation. Summation j is equals to 0 to m wj xj, right? Here in this particular case, m is the degree of polynomial and x is essentially an increase in power. So it could be from x, x square, x cube, so on till x to the power m. Now although y is not linear in x, because we start from x, we go to x square till xm, it is linear in parameters w, because we have w0, w1, w2 and so on. Hence it is linear for parameters w. Now as we saw in any learning algorithm, our goal is always to minimize the error. In this particular case, we define the error as given in this equation. Error of w is given as 1 by 2 n from 1 to n y xn w minus tn whole square, right? Now if we look at the graph here, we can see that for any particular input, say xn, we have a corresponding, so any particular input x set, we have a corresponding output which is y. Now this y, when we relate it to its corresponding ground truth, this is the error. So essentially the error function is the vertical distances between the data samples, which is the corresponding ground truth tn, and the output prediction, which is y. And similarly for each of these points, these are the vertical samples. When we look at the error equation, we write it as half the sum of squared vertical distances between the data points and the model output prediction. Okay, now before we we look at more complicated polynomials. Let's take a very simple example and look at low degree polynomials. So let's start with m is equals to 0. Now what we can see is y from the previous definition for m is equals to 0 would be only w0. For m is equals to 1 it would be this, right. We can see that the first equation for m is equals to 0 is essentially just a constant. So we can observe the output prediction which is given in the red curve, right, and we can observe that although this is a linear line, it does not actually fit the curve which is highlighted by the green curve, which is our goal, and hence it is a poor fit. It is an underfit to the data which is provided. If we look at m is equals to 1, we can see that it is w0 plus w1 times x, which is essentially a line. Now although it is a line, if we plot it and see it in the graph below, it does try to approximate some of these points. However, it is not a very good approximate overall to the curve. So for example, although this is a linear line, let us assume that my x cap, which is my test set, is highlighted here. If that is my x cap, then the model, or for m is equals to 1, it would essentially predict t as this, right, and we can see that there is a considerable error here. So this is not the most approximate or not the most accurate way to fit this curve. Okay. So essentially it gives us an idea that the high degree model could be used, which is using m as a higher number, not just 0 and 1, and for each m we can actually get an error and assess how does it fit to the curve. Now let us look at more degrees. So let us look at m is equals to 3. If we look at m is equals to 3, essentially our y becomes w0 plus w1 times 1, w2 times x square plus w3 times x cube. If we look at this particular equation, which is also highlighted by the curve, the first on the top left corner, we can see that green is essentially the true distribution of the training data, and red is essentially the output y that we are getting, which is approximating different data samples, and we can see that it is actually a very good fit. It captures the trend of sin 2 pi x, and essentially we do not even need to know the actual distribution. So this essentially is a very good fit. Now if that is true, let us try to increase the degree. So let us go for m is equals to 9. If we do as n is equals to 9, we essentially would have a very high degree polynomial which would be written in this particular, which could be highlighted by the bottom equation. If we do that, the corresponding plot is given as the plot below, right. As we can observe, this is a highly unstable and oscillatory kind of a curve, which is the red curve, which is essentially y, and if we look at the green curve, it is essentially the sin 2 pi x. So for m is equals to 9, which is a very high degree, we observe that the curve actually has very high oscillations, right. It does not really understand the data, or one way to comment about this curve is it has learned all the training data points, and hence it has a very strong fit to all these data points. However, it does not generalize to all the points. So for example, I take x cap as here, which is my test set. I would approximate the target as highlighted at the top of the curve, and that is not correct, right. So we observe that it does not actually have a good generalization to the new data or to the test set. Again, when we highlight test set, it is highlighted as x cap t cap. So for a given input x cap, we need, the model should actually identify t cap, and t cap should be very close to the green curve, right. Now this overall phenomena is known as overfitting, and this could also be related as having huge number of learnable parameters. However, when you have a huge number of learnable parameters, which is for m is equals to 9, we have about 9 learnable parameters which are w. The model actually memorizes the data and it doesn't generalize the data. We also observe that the model on the extreme edges of this curve, so let us take the extreme right edge and extreme left edge, we observe that in these scenarios the model actually learns the noise itself. So it is starting, or it has memorized this training set, but it essentially just learns the noise, and hence it is very distant from their true distribution. Okay. Now if we relate the learnable parameters or the degree of the polynomial on the x axis, and we plot the error on the y axis, where E RMS is given as 2 E star divided by n. So if we use this particular equation, where W star essentially highlights the most optimal set of weights using any particular learning algorithm. If we plot on this, or if we observe on this curve, the blue curve highlights the training set or the results on the training set, and the red curve highlights the training on the test set. So essentially any point apart from the training set that we saw, which is for 10 samples, other points, how does the behavior look like? Now for a model complexity m of 9, which is the 9th degree polynomial, where you have about 10 coefficients W0 to W9, it actually learns, or it actually fits all the training points exactly, which is something we observed in the last curve. However, the training, additionally the training is very low, or it essentially becomes 0. So if we observe the blue curve, as I keep increasing my m, or keep increasing my degree of polynomial, right, from W0 to let us say W3 to W6 to W9, I can observe that the error continuously decreases, and at m is equals to 9 it actually becomes 0, which is very good, right, because we want the learning algorithm to learn from the training data. However, we observe that the test set increases significantly, right. So again, if we observe the red curve, we can see that as I keep increasing m, it actually reaches a good sweet spot, and then it just increases. Now this actually makes us understand how the model behavior is, that for a very high degree of m, the behavior has large oscillations. The model actually fits perfectly on the train set, but it doesn't generalize on the test set, and this phenomena is something that we call as overfitting. It has overfitted on the data because it memorized the train set and it did not generalize to the test set. Now let us again take a look at this example, but from a numerical point of view. Now again, once we have y, which is given as wj xj, which is my learning algorithm, from this we would essentially get an error. Once we get this error, we would use, let us say, a standard gradient descent algorithm, and we would compute this particular equation, which is the gradient of error is 0. Once we do that, and once we solve this particular equation, we would get optimal set of weights and so on. So W star, right, we would get this set. Now essentially the goal for us is to understand what is happening with the optimal weights, hence we do not solve for this, but we know the values from the table on the left. So let us assume my m is 0, so essentially y is equals to W0 times x, right. Now if I solve this particular equation, which is the gradient, we would get the value of W0 as 0.19. Now I can keep increasing the value, and let us say that I do it for m is equals to 3, I would have certain values. Now one thing we observe even for m is equals to 6 is that all of these values are in a considerable range. So it's from 0.19 to, let us say, for m is equals to 6, the highest fluctuation it has is minus 25.43, and these are all weights which are having an influence on the test set, right. Now if we look at m is equals to 9 and look at the weights which are provided, we can see that these weights are not really in a bound compared to m is equals to 0 and m is equals to 6. So although W0 is more or less similar, all the other weights are at an extremely high magnitude, right. Now this is something which we observe even in the curve. For extremely high magnitudes, the weights actually have a very strong influence, right. So if I take a weight, if I take an input here, and if I just from the training set, if I try or if I want to get the value for x cap, the weights are so high, the effects of weights are so high that for this particular input the value actually is very, very high and it is not part of the curve. And this is why we have a very noisy curve for m is equals to 9, because the value of the weights are very high, they are not in bound. If the weights are not in bound, if I give any particular input, the corresponding output or t cap would be very, very noisy and not follow in this curve. Okay, so let's just see what is the influence of these weights. As the polynomial degree m increases, the coefficient's magnitude increases significantly, which we can observe from the table. For a very high degree, we have both positive negative values, however the magnitude of all is very, very high. As we saw in the curve, the model actually learns or fits on the training points exactly, right, but the model highlights a very oscillatory behavior, and the reason is that the model starts learning noise instead of the actual true pattern. Since it learns noise and due to the heavy influence of these weights which are very, very high in magnitude, there is a risk of overfitting. The risk of overfitting because it does not fit to the true curve, it does not fit to the sin 2 pi x curve, it gives a very, very huge fluctuation for the test set. Okay. Now for the same m is equals to 9 polynomial that we saw before, let us try something different. In the previous example, our training set n had 10 samples. So there were 10 random samples in the curve sin 2 pi x with certain noise. Let us try to do something different. Let us try to introduce n as 15 and n as 100, which is essentially we are trying to increase the training data from n is equals to 10 to n is equals to 15 and 100. Now if we again observe the curves for n is equals to 15, we see that the fluctuation is not that high, right. It is more or less trying to learn the data, and if I increase it to n is equals to 100, I can see that this fits perfectly, right. The fit is very, very good. I would not say 100%, but this is essentially a fit that we would want. And this highlights one more important point, which is the effect of the dataset size. A larger dataset would essentially reduce the overfitting for the fixed model complexity. So for an m is equals to 9, I actually need samples where n are 100, and that is important. If my n is just 10, then for m is equals to 3 polynomial is sufficient, right. So the key idea is more data will help in generalizing better, right. With more data we can safely use more complicated models, and actually with more data we can learn more complicated functions. For example, here we are only focusing on sin 2 pi x, however for an extremely complicated curve we could actually use more complicated models. Okay. And a general heuristic in this particular example is the number of data points should be about 5 to 10 times the number of parameters. Okay. Now let us also see the influence of regularization. So this is the error that we had defined earlier, which is 1 by 2 summation n is equals to 1 to n y minus tn whole square, right. Now let us add a regularizing term which is highlighted by the second part of the equation, which is lambda 2 norm of w square. If we write norm of w square, it is essentially W0 square, W1 square, W2 square till W9 square. Essentially because we are currently working for m is equals to 9, right. Now if I have this error, the goal of any learning algorithm is to minimize this error, right. So we saw this even in the earlier lectures. So my goal is to minimize E of W for all W and attain an optimal W, and this optimal W, once we learn, which is a set of from W0 star, W1 star and so on, would then be used for inference, right. Now when I am using a regularizer, or when we define the regularizer, we are essentially trying to minimize these values as well, because in this equation the last term is also included. So we are doing a minimum of even lambda by 2 norm of W square, right, and lambda is the penalizing function. Lambda influences how much should the weights be decreased, right. Now again let us go back to these curves. So for different regularization strength, which is lambda, we have different smoothing of the curves, while without any regularization we had an oscillatory behavior for m is equals to 9. If I have log lambda as minus 18, and then we would get a lambda value, and that lambda value could be plotted here. We see that for the same polynomial, which was extremely oscillatory, we now have a very good fit compared to what we saw earlier, right. But let us go to an extreme end, and let us say ln lambda is 0. In this particular scenario, the value of lambda is very high. If the value of lambda is very high, essentially these weights, the value of these weights would be very low. Why? Because we want to minimize this error. To minimize the error with a very high penalizing function of lambda, the values of these weights W0 to W9 would be very low, and essentially if these values are very low, they sort of behave like a linear function, right. Hence we observe that the output predicted red curve is essentially a line, right. So although regularization has very strong influence on the learning ability of, in this particular example, of curve fitting and even on training models, the value of lambda is also equally crucial. Okay. Now let us do a direct comparison for the m is equals to 9 polynomial with different lambda. So in the first example we see that there is no regularization, right. So we can see that it is an extremely oscillatory behavior. Next we take log lambda is equals to minus 18, and we see that it is quite a good fit, and at the other extreme we have the value of lambda is very high, right. So in the middle we have medium lambda, at the right we have lambda value which is very high, and at the left we have lambda value which is essentially 0, so it is very low. So a moderate lambda, which is lambda is equals to minus 18, reduces overfitting and hence is a much better approximation of the true function, which is sin 2 pi x. For a very large lambda, it is actually termed as over regularization, which is the regularization is so strong that it actually starts underfitting on this particular case. And lastly, the effect of coefficient. Regularization reduces their magnitudes, and hence we see the direct effect on the curve fitting part. So the takeaway is, we want to find a sweet spot of lambda so that we get a curve which is in the middle, which is a much better approximation rather than the two extremes that we see either on the left or on the right. Okay. Now let us again take a look at these values, right. So for lambda is equals to minus infinity, which is essentially lambda value as 0. Then in the table we observe lambda log n is minus 18, which is a medium value of lambda, and then we have log lambda is equals to 0, which is essentially lambda value is very high, right. So I will write it as very high. Now this is the same, it is a similar table that we saw even in the earlier case, where we try to minimize the error, which is based on this. We want to satisfy this particular criteria, and from this particular criteria we would essentially get the set of the most optimal weights for our fitting. Now as we observe, when lambda is essentially 0, essentially there is no regularization, we see the effects to be very similar to the previous case for m is equals to 9 polynomial, right. We can see that the magnitude of these weights is very high, and this is something that is going to influence the curve fitting performance. Now when we have a moderate or a meaningful lambda, we actually see that these values are more or less in bound, they are not going all over the place, and hence it would not be that noisy. And let us then go to an extreme where we say the lambda value is very high. In that particular case, the weights value is very low, right. So if I wanted to write in the for the last case of lambda is very high, after we get these weights, we can write y is equal to w0 star plus w1 star x1 plus w2 star x square and so on. Now in this particular case, we see that the values for other w's are so less that the influence of that polynomial generally just focuses on the linear part, because for the other parts the value is very negligible, right. And this is also something we see in the curve. So model complexity is essentially a critical factor in performance. If my data set is only of say n is equals to 10 samples, it is better to take a smaller degree of polynomial rather than a much larger model, right. So again, the need to choose an appropriate complexity is always crucial. Along with that, the regularization and the type of lambda is equally crucial. Okay. Now one particular thing that we have been doing is we have been trying to train our model on the train set, and we have been trying to validate it on the test set or validation set, right. And this is something that we have been terming as generalization. The performance is, the goal is to train on the train set, and for the holdout set or the test set, which we have been defining as x cap comma t cap, which could be any point on the curve, we want it to generalize. Okay. Now coming back again to the graphs which we observe on the right, we can take a look at the train and test error. So in this particular curve which is on the right, we can see that on the x axis we have lambda log lambda, which is essentially the effects of regularization, and on the y axis we have the RMS error, right. We see that as the lambda is very small, which is let us say around -35, we can see that the training loss, the training error is also very small. As we keep increasing the lambda, we can see that the training loss actually has an influence, and essentially it overshoots, right. This is a very similar thing we observe even for the test set. The test set actually also has a sweet spot of lambda. Any other values of lambda actually increases the test error, right. And this is what we call as the most optimal part of lambda. So in this curve, any lambda that I choose in this particular range, that is from let us say -35 to -25, would give me a meaningful set of weights, right. But anything at an extreme end would either make the weights very high or make the weights very low, and hence we need to find out a sweet spot of lambda which can be used for regularization. Okay. Now we have seen one particular case of using loss based regularization. There are also other several ways of controlling the capacity of single layer neurons or multi-layer neurons so that we do not have overfitting. The first part is the loss based regularization that we saw earlier, and that we will also see in the subsequent slides. We also have something known as max norm constraints, which we will highlight now, and finally the dropout. Now in max norm constraints, essentially what we are trying to do is we are trying to enforce an absolute upper bound on the magnitude of the weight vector of every neuron. So if we relate it either to the curve fitting problem, or we relate it even to the single or the multi-layer neuron and the multiple examples that we saw, essentially the max norm constraints, what it is trying to do is it's trying to clamp the weight vector to satisfy this particular equation. So essentially we have, so if I write this equation, it would be W0 plus W1 square plus W2 square. Let's take it to the 9th degree polynomial we saw, right. This should be less than C. C is a scalar number, it is a constant. So let's take an example and make C as 10. So now this criteria has to be satisfied during the learning algorithm, and for any particular reason if this particular criteria is not satisfied, then we would clamp the values. We would maybe say that okay, let the weights attain a maximum threshold, but it should not bypass this particular criteria. Clamping the weights is, let's assume that I have a threshold of W0 as 100, as let's say 2. So any time this constraint is violated, I can just make W0 as 2, W1 as 2 and so on. This is just an example, right. So the typical values of C are on the orders of 3 to 4. Now max norm constraint is essentially, the goal is that the network should not explode even when the learning rates are too high, since the weights are bounded, since the weight needs to satisfy this particular criteria, which is the norm of the weight should be less than a particular constant. The second part is the loss based regularization, which we have been analyzing in the curve fitting example. So the error can be defined as the actual error that we have been seeing, which is due to the output prediction, plus a penalizing function on the weights, which is given as lambda by 2 norm of W square. Now there could be different types of regularization based on the different types of norms that can be used. So let's say we use an L0 norm, then the equation would be modified as error is 1 by 2 n from summation n from n 1 to n y minus t whole square plus lambda times norm of W norm of 0. The second could be using L1 and L2 norms. So essentially we could modify this equation as lambda 1 times the norm of W norm 1 plus the norm 2 of the weights. Similarly, we could also have different type of regularization using either of the norms. We could just have an L2 norm, which is the error term, plus lambda by 2 the norm 2 of the weights, or we could just have an L1 regularization, which is essentially what we saw earlier. Okay. Now the previous regularizations that we saw were mostly focused on the weights. So we are training the model and we are putting certain constraints on the weights itself, right. Now there is also a regularization technique which is defined as dropout, which is essentially a technique to that is used during training, right. So let's take a standard neural network and let's say that we are using a particular learning algorithm, right. So as we saw, even in our case, we had corresponding inputs and we had corresponding outputs, and for each particular input the input would be fed and we would essentially train certain weights along the way, right. So all of these weights would be updated using gradient descent. Now when we are using simple vanilla standard neural network training, all the neurons are activated, so all the neurons actually have the weights updated. However, sometimes what would happen is certain weights would be higher in magnitude. This is also something we saw in the curve fitting example, where W0, W1, W2 were in a considerable range, they were 2-digit numbers near to that, but the other weights, which is W4 W6, W7, W8, W9, they were very high values, right. So in those particular example, those weights would essentially have a dominant effect while training. So let's say we have certain other weights which would be very crucial during the training and would have very high magnitudes, and due to that you would have certain neurons which would have more influence during the there would be certain neurons which would have more influence during the learning parameter. So during an inference part where I pass x cap and I want to calculate t cap, only those pathways would be excited, and other pathways, since the weights is very nominal, their effects would not be that significant. Now to avoid this is something why we use dropout. So in dropout it's a very simple phenomena. While training, dropout is implemented by keeping only certain neurons active with a probability of p and setting other ones to 0. So after applying dropout, let's say for example on the first layer, with a probability of p we would deactivate certain neurons. Similarly in the second layer we would deactivate certain other neurons, and so on, right. So for each layer, if we introduce dropout, in each layer with a probability of p, certain neurons would be turned off, right. And if that happens in a random manner, then the phenomenon that we just discussed on the left would most likely not occur, because those weights would not always be part of the learning algorithm, and which is why the weights distribution or the magnitude of the weights would be meaningful. So essentially dropout is turning off certain neurons during training in a random fashion. However, during inference there is no dropout applied. So during inference all the neurons are active and the weights are passed, or the forward propagation happens throughout all the neurons, right. Okay. Now let's just quickly summarize what we saw in the curve fitting example, right, because essentially that was just an example. The goal of curve fitting, or let's say a generalization point of view, let's assume my x axis is input and my y axis is the output. Now we have certain training sets which are highlighted by the cross here. Similar to the example we saw, there is an underlying distribution which is given by this curve. This is the underlying distribution. The goal for us, this is the distribution. The goal for us is the goal for any learning model, which is essentially a single layer neuron or any other curve fitting model which has learnable parameters, is to learn the true distribution of this curve, right. So that at points like the generalization points, which could be highlighted as x cap, which is the test set, we actually come across the actual value from the underlying distribution rather than a value which would have considerably higher error, right. This is something that we would want to avoid. Now generalization is influenced by three factors: the size of the training sample and how representative the training sample is. Thus influence of the size of the training sample is something we saw in the curve fitting example, where we had n is equals to 10, but for n is equals to 15 or 100, the model with more polynomial for m is equals to 9, actually the learning was much better. So the size of the training sample matters, and the representativeness of the training sample also matters. For example, in this particular curve, if all of my training samples are populated in one particular region and not in the other region, then the curve would not, then the curve fitting would actually be a little bit biased. So we would have a very strong estimate here, but in the other part of the network our estimate would be very noisy. The architecture of the neural network also matters. We saw this also. For m is equals to 0, 1, 2, 3 till m is equals to 9, we saw the influence of different when different weights are added. So different weights in the sense, if I have W0, W1, we saw what happened. We saw what was the most optimal fit, which was m is equals to 3 or 4, and we also saw what would happen when m was 9, which is a very high degree polynomial, and the physical complexity of the problem at hand. So this is something that we will discuss much later on, why the physical complexity plays a role also, right. Okay. Now overfitting is something that we saw where the model actually has too many input output examples. It actually ends up memorizing the data, right. So once it memorizes the data, which is essentially highlighted by these crosses as in the curve, its generalization performance is affected. So for a test set which is x cap comma t cap, and this could lie anywhere on the curve, this generalization is not very accurate. Okay. Now certain causes of overfitting are, it could also be due to the higher number of hidden units or learnable parameters in advance. So if we did not realize the complexity, we could have chosen m is equals to 9, and that would have led to overfitting. If we have too less of parameters, then it leads to underfitting, which is essentially not able to learn the actual data distribution. Certain solutions that exist is, we could use something known as cross validation set, or we could use as weight decay, which is decrease each weight by some factors on every particular epoch. Okay. So let's just quickly summarize the model complexity. If we see the first part, which is the underfitting part, we can see that this particular curve actually highlights the true distribution of the data set. This could be highlighted to m is equals to 0 or m is equals to 1, which is essentially just a linear line. It has very low variance in the sense that if I have a training set which is highlighted by that dot, let's keep it at x1. If I add certain variance, if I add certain perturbation to this particular input, let's say I am trying to see its performance at x cap, which is very close to x1, there is not much variance. We see that it doesn't fluctuate a lot. So the value of the target would more or less be similar, but it has a very high bias in the sense that it is very far away from the actual distribution of the training set. Now let's take, so this is the underfitting. Let's take the different example, or the example on the other end, which is the overfitting case. In the overfitting case, we can see that there are a lot of training examples here, right, a lot of training samples here, and we can see that the graph is oscillatory in nature because it has lot of learnable parameters. This corresponds to something which we saw as m is equals to 9. Now in this particular case, the variance is very high. So you can just see this curve. If I plot a point here, a point that is very close to this, there is a very high variance. So it is very oscillatory in nature, right? And it actually has low bias in the sense that it is very close to the actual distribution of the data. However, it is very oscillatory, so it's not the most optimal, right? And the ideal fit would be a balanced bias and variance. So it should have a bias variance, which is a small change in the x should not result in a very drastic change in the target, which is what we observe here. And it has a balanced bias, which is essentially, if I see the dotted line, which is the dotted curve, and the approximated curve, it is very close to each other, right? So hence this also, so again we see that an ideal fit is something that we want to compared to an underfitting or an overfitting model. And again, this is not only our model, this also depends on the data set we saw, it also depends on the model complexity. Lastly, let's go quickly over the process of cross validation. So let's assume that we start with the holdout method, which is we split the data sets into training set and validation set. Now let's actually go to the k-fold, which is, so in k-fold we divide the data set into k equal subsets, which is highlighted here. So we have n is equals to 1 to n, k is equals to 1 to k is equals to 4, right? We have these particular 4 splits as observed in this figure. Now one way or the way to use in k-fold cross validation is, once we divide the data set into k equal subsets, we train the model on k minus 1 subsets, right? So let's assume that I take k is equals to 1 to 3 and train our model, and we try to validate the model on k is equals to 4, right? And we try to repeat this multiple times so that we have a distinct set. So for the first example, let's say I took k is equals to 1 to 3, my val set was 4. In the second set, let's say it's k is equals to 1 to 4, val set is 3, right? and so on. We can try to repeat this trial. Once we do that, we can take the average of the validation loss across the k trials, and this actually has its advantages in the sense that it provides a reliable performance, since we have tried to evaluate it on multiple folds rather than focusing on a particular fold. One disadvantage is that it is computationally expensive. The model has to be trained k times, the model has to be evaluated k times. Okay. Lastly, let's take a look at the early stopping phenomena. Now, if we relate it also something to the polynomial fitting example, the goal is to train a model for a period. We can call it as an estimation period, or we can just call it as the training period, right? We want to pause the training and we want to validate the error over a separate data set. So we could follow a k-fold manifold kind of an approach, right? So the training set is given as x comma t. The validation set could be highlighted as xv tv cap, because our test set was as an example of x cap t cap, right? So we have defined the train set, we have defined the validation set, and we are trying to train the model. Now if you observe the curve on the right, we can see that the training error decreases as we proceed with epoch. So we can see that the training error decreases. Now there is something very interesting that happens to the validation loss or the validation error. The validation error, essentially it decreases initially, which we can see from this particular example in this particular period. After this it reaches a minimum, and from this point it increases again, right? So it started off at a high value, it reached a very good minimum, and then it started increasing, right? The key insight is that if this particular increase is observed in the validation sample error, this indicates that there is an overfitting, or essentially the model has started learning noise instead of the training set. Now in this particular case, if we observe that the validation loss starts increasing, what approach we could use is the stopping criteria, which is stop the training at the minimal point of the validation error, which is this point, which we highlight as the early stopping point. If we use this, then throughout the whole training procedure, if we stop at the early stopping point, we observe that the generalization performance increases. So the performance on the val set, performance on the test set is increased. Okay. So to summarize, the lecture covered the curve fitting example. We also saw different degrees of polynomial from m is equals to 0, 1 to an extreme case of m is equals to 9. We saw the effects of regularization on the curves itself. We also observed what is defined as generalization. Finally, we also saw the effects of model complexity versus learning. Lastly, we covered cross validation and early stopping. Thank you.